What the heck? All right, everyone. Welcome to Thursday. So you can see the results of the test here. There, I know that that's like a pretty nasty thing to look at there. It shows all 14 students that are still in the class, all the grades for each test. I don't know where to begin. The gray chart is the grades for exam 3. I just got those finished up today. The average on exam 3 was an 84. And exam 2, the average was a 90. Exam 1 was 72. This is the distribution of A, B, C, D's, and F's. So we had a little bit fewer A's, but more B's than we did on exam 2, more C's than we did on exam 2, but we also had less fail. So anyway, this is what it is. The yellow are the class averages for each student. So of the 14, we only have 3 that are below passing at this point, and the rest of you are above passing. So that's where we are. Any questions? Questions? I do plan on sharing the solutions to the exam at some point, just not yet. So for now, just review, go back and look and see if you can figure out where your mistakes are or where they were, if you had any. The highest score on exam 3 was 105, which was the highest score you could get. Okay, that's it for that. Y'all ready to talk about more series? So we finished up last time. We were talking about, let's see, we were doing we had the comparison test, and then we did the limit comparison test, which seemed really nice. And you're kind of free to use whichever one you want, all right? But there's still a few more tests we need to discuss. I did have this little true or false question for you. So I'll give you a minute to just look at that. And then I'll just ask for a volunteer to tell me if you think that all of this is true or false. Yeah, why don't we do a poll? We'll do a poll. We haven't done a poll in a while. So yes would be true, no would be false. I'll give you another 20 seconds to give me an answer. Okay, let's say that's it for time. All right, so here are the results of the poll. Almost 50-50 on this one. Okay, so this is what I was trying to get across last class is that if you're looking at a series, right? If you're looking at a series and you look just at the sequence, right? A sub n. If you take that limit of that sequence and you get 0, the question is, does that tell you anything about the series itself? And the answer is no. Okay? No. You know nothing about the series. This is the nth term test. This is the pregnancy test, right? Just because the sequence goes to 0 doesn't mean you can tell me anything about the series. So this is false. So if this happens, right? If this happens, then we don't know anything. It may converge, it may diverge, all right? So I always say, like, this is the fundamental thing you have to understand, or else everything else you can't build off of this. If you don't get this, then every time you see a series, all you're going to be focusing your attention on is that. You're just going to be like, oh, that goes to 0, I'm done. That's not the case. All right. Any questions on that? So this is all false. All right, let's look at the next series that or the next test that we are going to use, and that is the alternating series test. But first I need to define, I'm going to define for you what an alternating series is. So an alternating series is a series that looks like this. You have a number minus another number plus another number minus another number plus another number minus another number, and so on and so forth. This continues. So it alternates, plus minus plus minus plus minus. Or you could have it go like this. You could start with a minus and then have plus and then minus and then plus and then minus. As long as it alternates, okay, as long as it alternates signs, then we call it an alternating series. So you could write it this way: sum n equals 1 to infinity of -1 to the n times a sub n. So what happens here is that you plug in 1, and in this case, if we plugged in 1, we would get a negative, wouldn't we? First term would be negative, and then it would be a sub 1. So that would be this right here. Then we plug in 2, it'd be -1 squared, which would be a positive, and then a sub 2, so that would be this. So this is actually equal to that one right there. How could we create this one up here, where we want it to start out positive? What would we put?
Sub a to the, or -1 to the n plus 1.
N plus 1. Yep, there we go, times a sub n. Good. So whenever we have an alternating series, we're always going to have this -1 to some power. That way we get the alternating to take place. If you go and you look at everything we've studied up to this point, okay, I'm going to flip to the formula sheet here. If you look at our formulas, the test that we just learned, the comparison test, notice that it said that the a sub n and the b sub n, both of these had to be positive, or else we can't use the test. In other words, you cannot use a comparison test if you have an alternating series. You can't use it, all right? You also can't use the integral test, because remember, the integral test requires that we turn the sequence into a function, and that function must be positive, right? So if it's alternating, it's not going to be positive. It'll be positive then negative, positive. So you can't use the integral test. The p series, well, p series don't alternate. P series don't alternate because you're plugging in n equals 1, so you put a 1 there, then a 2, then a 3, then a 4. You never have any negatives ever. So you won't have, P series won't ever have alternating in it, right? Now, geometric series you can, because that R right there, it could be a negative number. So what I'm getting at is we need a test. We need something that's going to help us deal with series that alternate. Okay, and we have the test. It's down here. It's an alternating series test. I'll write it down, but let's just get to an example first. So let's take a look at this example. Let's go sum n equals 1 to infinity of -1 to the n over n. So does this converge or diverge? I'm going to write this every time I want to say converge or diverge. I'm just going to write that so I don't have to write the words out, right? So does that converge or diverge? All right, well, let's write out the series first. Let's just write it out. If I plug in 1, I get -1 over 1. Then if I plug in 2, I'm going to get a positive up top, so 1 over 2. If I plug in 3, now I'm going to get a negative up top, so I'm going to say plus -1 over 3. And then plus 1 over 4, plus -1 over 5. Y'all following this? This becomes -1 plus a half minus a third plus a fourth minus a fifth plus ... Okay, so let's talk about the things that we've learned already. Nth term test, right? Pregnancy test. If we take the limit of this thing as n goes to infinity, you basically have bounded on top, right? The top's always been either -1 or 1, and then the bottom goes to infinity. That should go to 0. And since that goes to 0, that tells us nothing, right? We know nothing about it. It's not a geometric series because we don't have an r to the n. Well, this n down here is what's causing it not to be geometric. So we don't have geometric. Is it harmonic? What do you think? Harmonic was what? Constant over linear, right? That's what a harmonic was. -1 to the n on top is not a constant because it keeps changing, right? I mean, sometimes it's 1 and sometimes it's -1. In order to be harmonic, what's up top must always be the same number the whole time, right? So it's not harmonic. It's not telescopic either. It may look like maybe some of this cancels, but nothing does, okay? Like we don't have like this 1/2 cancels with something down here. That's not happening. Comparison test. Can we use a comparison test? No, comparison test says that your original series, that the sequence, the part in yellow, has to be positive, and this is not always positive, so we can't use a comparison test. So we're kind of stuck at this point, all right? We're stuck. So here comes the alternating series test. I'm just going to write it out. I'm not going to bring it off the formula sheet. So the alternating series test which I will start to abbreviate AST, is this. It says, given a series, right, where you have something alternating. Now, this might be -1 to the n, or it could possibly be n plus 1 up there. It doesn't matter if it starts negative or positive, okay? It doesn't matter. Just as long as we do have alternating happening. And then next to it, you have the formula sheet uses B sub n instead of A sub n. Don't know why, but that's what they do. So let's say we're given this series. All right, what we do to test if this converges is this. If, one, we have two things that have to happen. If the limit as n goes to infinity of B sub n equals 0, and 2, B sub n is greater than B sub n plus 1, eventually, then that series converges. So that's it right there. All we have to do to show an alternating series converges is to show that these two things are true. Right, so let's go ahead and do this. All right, we're going to do this for this series up here. So I'm going to write it down here for us. So we have this example where we have sum n equals 1 to infinity of -1 to the n times 1 over n. Or sorry, yeah, I split it up. Do you see I took that n on the bottom, I just split it off to the side as 1 over n? That's the same thing, right? So this right here, this is our b sub n. It's the part of the sequence that doesn't have the alternating happening. What we need to do is, one, let's show that the limit of that is 0. So let's see if it is. The limit as n goes to infinity of 1 over n, well, that is 0, right? We know that's 0. That's an easy one, right? Fixed over infinity, we know it's 0. Next thing I need to do is show, what does this mean? What does b sub n greater than b sub n plus 1 mean? That this sequence is doing what?
The next in the sequence.
The next one in the sequence is what?
Increasing.
Smaller than the previous one? That means it's decreasing. So really, this second thing is to show that this is a decreasing sequence. So for 2, I need to show that 1 over n is bigger than 1 over n plus 1 eventually. So is this true? Well, we do that kind of like cross multiply thing. We go n plus 1 bigger than n. And subtract n from both sides. We get 1 is bigger than 0. That is true. And so it is decreasing. So that's it. According to the alternating series test, therefore, this series does what? What does it do?
Converges.
Converges. We don't know what it converges to. Okay, we don't know what it converges to, but we know it converges.
So for this test, we can only know if it converges, but we won't know if it diverges.
Yeah, that's right. So like, let's say that this limit wasn't 0. Monato's bringing up this very good point. Let's say we did this and it wasn't 0. We would not say, oh, then it diverges. We would just say the test failed. Okay. If these are both true, then it converges. If either one of these are false, the test has failed. Okay. Now, let's, what we just did is actually kind of interesting if you think about what we just showed. Let's do a comparison of these two series. I want you to look at these side by side. Let me do a new page. So look at these series. This one versus this one. So the one on the left is just 1 plus a half plus a third plus a fourth plus a fifth plus dot dot dot. The one on the right is -1 plus a half minus a third plus a fourth minus a fifth plus dot dot dot. So there's a difference between these two, right? The one on the left does what? Converge or diverge?
Converges. No, on the left.
On the left, this one.
That's what we just did. It converges.
No, we did this one. We did this one. Right? This was an alternating series. This one's not. What type of series is this?
Harmonic.
Harmonic. What do harmonic series do?
Diverges.
Diverge. So this is a divergent because it's harmonic, right? This one is an alternating series, and we just showed that it converged, didn't we? We did that using the alternating series test. So these look very similar, but having every other one of these being subtracted has a huge impact on things. It actually makes this thing converge. as opposed to over here, when we add them up, we get divergence. Questions? We're gonna do another one. Okay, how about this one? That one's no good. Yeah, this one. Okay. How about this one? Sum n equals 1 to infinity. Let's do -1 to the n plus 1 times n over the square root of n cubed plus 2. When I see an alternating series, the first thing I always think of is alternating series test, because the test for alternating series is very nice. I mean, it's actually not that bad of a test. So I'm going to run the test. Here we go. First thing, I'm going to take the limit as n goes to infinity of what? What am I taking the limit of?
N over square root of n cubed plus 2.
Yep, I'm doing just the part that's not alternating, right? Just the piece that does not include the -1. So I need to do the do that limit. Now, I noticed on your take-home test that some of y'all did this by L'Hopital, and it turns into a nightmare if you try L'Hopital on this. The other, I think, nicer approach to this is to try and get rid of this n cubed by multiplying the top and bottom by 1 over the square root of n cubed. 1 over the square root of n cubed. If you do that and go here and then distribute this through here, you get this. Okay, so on the top it's n over, I'm just going to rewrite that as n to the 3/2. That's what the square root of n cubed is. That's the top. And on the bottom, when this goes here, I'll do it on the side here, the n cubed goes underneath here. So you wind up getting, well, I can do it down here. You wind up getting this n cubed over n cubed, and then plus the 2 over n cubed. So that's just me algebraically putting this together with this underneath and distributing the n cubed through, the 1 over n cubed through. And what winds up happening there, if you need help on that, if you're not understanding that step from here to here, just get with me later on that. On the top, we get 1 over n to the 1/2. So that's what happens when I simplify this. And then on the bottom, I get square root, square root of 1 plus 2 over n cubed. And now when I let it n go to infinity, I get 0 here. On the bottom, I get the square root of 1, because this 2 over n cubed goes to 0. So we just get 0. So this limit is 0. So far, the first part of the alternating series test is confirmed. Now, I need to show that this is a decreasing sequence. So I need to show that, like we did in the previous one, where was it? Right here. We showed this. So I need to show that. So I need to show that the original sequence is bigger than that sequence when I plug in n plus 1. So I have to plug in n plus 1 everywhere I see an n. So that we need to make sure that we can show that that's true. That looks like that might be kind of ugly to do this. Would y'all agree that that might be kind of bad? Because we have that square roots in there. I mean, we could mess with it algebraically, but I'm going to kind of like ditch this idea. And what I'm going to do is I'm going to look at just n over this. And I'm almost going to look at it like a function. And then I'm going to take its derivative and I'm going to try and show that it's negative. And this we've done before, right? Anytime we want to show something is decreasing, we just take its derivative and try and show it's negative. So I'm gonna take derivative of this. So I'm gonna do a little quotient rule here. Derivative of the top times the bottom. Minus, okay, derivative of the bottom is gonna suck. But the derivative of the square root of something is 1 divided by 2 square roots of that something times the derivative of what was underneath the square root, which is 3n squared, times the original numerator, or yeah, the original numerator, which is this, and then all of that over the bottom squared. So when I square the bottom, the square root goes away. So there's my quotient rule. And I need to somehow try and show that this is negative all the time. Not pretty. Maybe we should have stuck with the inequality. I don't know. Maybe it would have been better. Okay, so there we go. That's where we are. I just cleaned this up. I brought the 3n squared times n. I brought it up top here. That's there. I got rid of that 1. And so now I'm going to show that this is negative. Now I'm not even going to look at the denominator because I know the denominator is always positive, right? N cubed plus 2, that should be a positive number. So I'm really more concerned about this thing up top. I need to show it's negative. So I need to get a common denominator. I'd have to make that this over 1 and then introduce a 2 root n cubed plus 2 over a 2 root n cubed plus 2. And when I do that and I put these numerators together, I should get 2, and then the roots cancel out, so I get n cubed plus 2, then minus the other numerator, 3n cubed, and then all of that over the common denominator, which would be the 2 square root of n cubed plus 2. And remember, that's just me doing this, but I'm not even going to look at this because I know it's positive. Any questions? I'm not going to look at this now because I know that's positive. N cubed plus 2, take the square root, that's got to be a positive number, times 2. So I just need to resolve this top piece. That turns out to be 2n cubed, just distributing the 2. So 2n cubed plus 4 minus 3n cubed, that turns out to be 4 minus n cubed. Now, is that always negative? Not always, right? If you plug in 1, you get 4 minus 1, that's going to be positive. But once you plug in a number like 2 or 3 or 4, this will be negative eventually, right? And this is what I was saying earlier about eventually. We don't need this inequality to be true all the time. We just need it to be true from some point on. So anytime n is bigger than 1, that's when this will be true. Y'all agree? So we have an alternating series. We took a look at the part that's not alternating. We took its limit, it sucked, but we showed it was 0. And then we showed that it was decreasing by taking the derivative of it, looking at it like a function and showing that the derivative was negative. So we've shown everything we need to show. Therefore, that thing converges.
I see the bottom again.
Yep.
Would you ever give us a problem that we would have to go like, we'd have to plug in like an insane number to get the,
No. To figure out that it eventually did.
okay, yeah.
No. It would be something. It'd be something where it happens in the first, 1 or 2 values of n. I mean, could I make one up like that? Yeah, but I'm not. I mean, I wouldn't do that unless it were a take-home test. Now, if it were a take-home test, that's different. All right. Do you get the gist of the alternating series test? You recognize it's alternating, and then you show these 2 things. If you can do that, you're in business. Now, the alternating series test, let's look at it on the formula sheet just so we can say we did. So it says if you have some, oh, they use A sub n here. I think the book uses B sub n. I'm sorry. Doesn't matter what we call that. This is the positive part of the sequence. So as long as it's decreasing, this is what it meant to be decreasing. And as long as the limit of that thing goes to 0, then it is going to be convergent. And I've never liked this, but this says for every k. I've never liked that on this formula. It's actually not for every k. It has to hold eventually. It can be increasing for a little while, but eventually needs to be decreasing. Not quite sure why they put that in there, but doesn't have to hold all the time.
Is the inequality greater than or equal to?
It can be equal, but if it's equal, then you're basically going to be looking at a constant, a sequence that would just be like the same number over and over and over. It wouldn't be decreasing, it would just be flatlining. It would just be the same value the whole time.
But it would still work.
It would work, yes, it would work. But if you think about this, then this limit would not be 0. Because it'd be the same number over and over, unless this was 0. Unless this was 0, but if this was 0, then the whole thing is 0, and then it's a boring thing. There's nothing happening. It's a series where you're adding up 0 plus 0 forever. So I don't usually put this equal because we're never going to see that. Like we're never going to have two things be equal. But technically, you could have it. All right.
Okay.
Good question. Good question. All right. So now we move on to the next thing. We're almost through this. Well, now we still have a little more. The next idea here, and this has always caused students a little bit of issues because of the language here. So I'm going to give you a definition again. A series sum n equals 1 to infinity of a sub n is said to be absolutely convergent if, okay, so that's what we're defining. What is what does a series being absolutely convergent mean? Well, if the sum n equals 1 to infinity of the absolute value of the sequence converges. So if you start out with a series, no matter what's going on in here, no matter what the sequence is here, okay, no matter what it is, if you take the absolute value of that sequence and you're able to show that this thing converges, then that means we say that this guy is absolutely convergent because it converges when you take its absolute value. Let me give you an example. Is this absolutely convergent?
I think because it's bounded on the top, and if it goes to infinity, it goes to 0 then.
I'm going to break out the whip. I'm going to break out the whip today.
Well,
Oh yeah, 0.
If you take the absolute value of the top, then that just stays at 1.
Okay, yeah, so let's stick, the question was, is it absolutely convergent, right? Is the series absolutely convergent? So this is what we need to check. What happens to this, right? So let's take the absolute value of this. CJ, you're on the right track here. If we take the absolute value of that, then the -1 to the n no longer matters, right? No matter what comes out, -1 or +1, you take the absolute value, it's just going to be 1. So this is the same as this series. isn't it? And can you tell me what this series does?
Converges.
Converges.
Why? Why?
P series.
Series.
This is a P series, good. This is a P series with P being 3, which is bigger than 1, therefore it converges. So what does that tell us? If the absolute value, right, we're looking at this series in yellow. The question was, is the series in yellow absolutely convergent? So we took a look at its absolute value and we found that that series was convergent. If this is convergent, then we will call this one absolutely convergent. And all it means is that when you take the absolute value of this series, the absolute value of it converges. Does this mean that the series in yellow is convergent? No, it just means that it's absolutely convergent, right? All right, let me do another example.
What is the difference between the two?
You'll see, I'm going to do another example I think will help illustrate how things are different, like what it, here, let me do the example. Okay, how about we do this one? Is this absolutely convergent? So what do we check? We need to take sum n equals 1 to infinity of the absolute value of -1 to the n over n. But when we take the absolute value, the -1 on top no longer matters. It just becomes 1 over n. Is that convergent?
That's harmonic, right?
Harmonic, right? That diverges, right? So what can we say about this? Is it absolutely convergent?
No,
Absolutely divergent.
It's not absolutely convergent. No, we actually don't have a definition for absolute divergence.
So does that mean this test fails if it is a
Nope.
test?
Nope, doesn't mean the test. So we have to go to the definition here. The definition, to be able to say that a series is absolutely convergent means that the absolute value of the sequence, when you take that series, it converges. If this doesn't happen, then we can't call it absolutely convergent. We need this to happen to be able to say it's absolutely convergent. So all we can conclude here is that it's not absolutely convergent, right? It's not absolutely convergent.
So you will ask us if it's absolutely convergent on the test.
That would be a specific thing where you
Right.
have to go and check this. Because here's the thing that's confusing, okay?
Okay.
If you're not already confused, here's what's confusing. Look at this right here, our original series. Is it convergent?
looks like the geometric theory.
No, because
top.
if we do AST, we would have 1 over n, and I don't think. Oh,
Wait a minute, didn't we just do that problem?
no, it does converge. Never mind.
Yeah, isn't that this problem right here?
Yeah. Yeah.
Right, isn't that the same problem? And didn't we show that it converged?
Right.
See, and this is where I think the language gets confusing, because I gave you a series and I asked you, is it absolutely convergent? And you said, nope, it's not absolutely convergent. And then I asked you, is it convergent? And you're like, yep. So it seems like, to me, the word absolute, like, to me, when I think absolute, I think like total, like universally, it's universally convergent, but that's not what they mean by absolute. They mean the absolute value, and that's it. That's all you're looking at. So I just gave you an example of a series that is convergent because the alternating series test, or I'm going to say here, yes, it is because of the alternating series test. So I just gave you an example of a series that is convergent but is not absolutely convergent. Y'all see that? Now, we do have a theorem that might help us here. Theorems can sometimes save our brains a little bit. The theorem says, if you have a series, if that series is absolutely convergent, then the series itself is convergent. Another way to say this is that absolute convergence implies convergence. So if you converge absolutely, you must converge. If the series converges absolutely, then the series itself by itself must converge. So if we go back and we look at this series here, the one that we started this conversation with when we started talking about absolute convergence. If we take this one right here, is that one absolutely convergent? Well, what do we do? Where is it? Right here, this one right here, right? Is this absolutely convergent? We went through, we took the absolute value, said that's a P series, it's convergent. And therefore, that's absolutely convergent, yes?
Yes.
Okay, so this one, this is absolutely convergent. What does that mean? That means that the series by itself, right? This series is convergent. That's what this theorem is saying. If you have absolute convergence, then you're guaranteed to have convergence. Look at this problem here. This one right here. Did we have absolute convergence? Did we?
No.
No. Right? We didn't have absolute convergence, which means we can't use the theorem, because the theorem says if you have absolute convergence, then you're guaranteed to have convergence. But if you don't have absolute convergence, you don't know. You don't know what's going on here yet. I know it's a little weird. Let me try and think of.
So here I am asking.
Go ahead.
Here I am asking the same question. What's the difference between absolute convergence and convergence? Like, is there any like graphical difference, or like as in like the plot, the points we plot, or?
Okay, yeah, maybe I can do it this way. Let's take that specific example. Okay, -1 to the n over n. Let's take that one. Okay, if we were to, let's just look at the sequence itself right here, this sequence. If we were to look at that sequence and plot it, when we have 1, 2, 3, 4, let's say 5. Okay, when we plug in 1, we get -1. So we'll be down here. Then we plug in 2, we get +1/2, then -1/3, then +1/4, and then -1/5, right? When we start adding these up, right? When we add these up, we take that value, whatever that is, that's -1, and we add to it 1/2, and then we subtract from that 1/3. When we do that, it converges, right? It converges. Because, well, we did this with the alternating series test, didn't we? Now, let's look at this. Look at the absolute value of it, right? The absolute, I shouldn't have done that in red, but the absolute value of it is basically this same picture with
But only
everything on the
positive.
positive side this time, right? And it turns out that for this particular series, this one, when we add those up, that diverges, right?
Because it keeps adding on.
Yes, keeps adding on, but it's the fact that it's linear on the bottom that makes it not add up to, not converge to something. So when you're given a series, right? that alternates, when you're given a series that alternates, that picture is going to look something like this, right? It's going to be top, bottom, top, bottom, top, bottom. To say that it converges absolutely means that when you look at that series absolute value, when you look at the absolute value of that series, it's all of those same points, but all positive, right, Minato? Yes, they're all
Right,
up here now.
right.
So if, Minato, if I tell you that all of those converge, right? And this is, you're adding them all up and they're all positive numbers, then wouldn't you agree that if I did the same thing, but then I subtracted some of them, this should definitely be a smaller sum, right? Because
Right.
instead of having all positives right here, which converge, now I've got positives mixed with negatives. So if that converges, then this has to converge. That's what the theorem is basically saying. If you've got absolute convergence, it forces that one to converge also. Does that help?
So
Yes, thank you.
yes, so absolute convergence means that the series itself converges, but the series itself converging does not guarantee absolute convergence.
I couldn't have said it better. That's exactly right. Yeah, I don't even know if I can repeat what you said, but that is perfect. Yes, exactly correct, what you just said.
Okay.
Okay. All right. Let me give you another example. This one's going to be weird. Does this converge or diverge? I'm not talking about absolute convergence right now, just asking about convergence. So is this an alternating series? Is it going positive, negative, positive, negative, positive, negative?
Yes and no. I think yes, because sign is bounded between -1 and 1.
Mm-hmm. But is it like when you plug in 1, do you get a positive, and then when you plug in 2, you get a negative? And then is it doing that? I have to show you a picture, I think.
Okay.
Let me see here. Wrong one.
I think it would converge.
Okay. So here, let me show you what that looks like. Sine n over, what was it, n squared? Ah, damn it. Okay, so look at this. Do y'all see the that when you plug in 1, you get a positive number, and when you plug in 2, do you see you get a positive number? And then when you plug in 3, it looks positive. When you plug in 4, you get negative, then it looks negative, and then maybe it goes back up positive. Do you see that it is switching, but it's not like positive, negative, positive, negative, positive, negative, positive, negative. This is not an alternating series. It is not, because it doesn't switch back and forth immediately one after the other. Are y'all clear on that? So we cannot use the alternating series test here. So watch what I'm going to do. You got to see me do this first time. What I'm going to do first is I'm going to take the absolute value of it. When I take the absolute value of it, I really only need to take the absolute value of the top. Okay. Now check this out. Well, let me write this down. So what I did here is I took the absolute value of the series. And now I'd like to know, does this converge? Because if this does converge, what can you tell me about this? If this converges, what can you tell me about this?
Then this
That
converges
also
too.
And that
converges as well.
converges also, okay, by the theorem I just gave you. But I have to still show that this converges. And no, I'm not going to just take the limit and let n go to infinity and say this is bounded over infinity, which goes to 0. That tells you nothing, right? So watch what I'm going to do. I'm going to do a comparison test now. I'm
So
gonna
you
com-
just only use the absolute value for the sign. You didn't put the n square in the absolute.
Well, I could do it here, but see, n is always a positive number. So having an absolute value around it doesn't change the fact that it's positive,
Okay.
because
Yeah.
n is always positive. So I only need to really look at the top. Now, here's the thing. I'm going to compare it. Now, can I use a comparison test right now? Yes, because comparison test requires that your series be positive, right? And I could not have done a comparison on this because this has negative pieces in it. So I can never compare to this. But if I take its absolute value, I can compare to this because this has nothing but positive numbers. Now, what am I going to compare it to? I don't know. I'm going to go with, oops, go ahead. What?
1 over n squared?
Yeah, let's go with 1 over n squared. Why? Because you know what? I mean, the sign n, that just fluctuates. 1 over n squared is like the dominant thing here. This is a p series, right? This converges. So how would you like to do this? We have two options. We can do the inequality, or we can do the limit comparison. What would you prefer?
Limit.
Limit? All right, let's do the limit comparison. So I'm going to take the limit as n goes to infinity. So for those of you who are like, what the hell is going on here? I'm going here, and from last class, I said these two are kind of clumped together, but then at the end of class, I said, we've got this one too. And this one actually turns out to be pretty nice. So that's what I'm doing. I'm going to take this limit, and I'm going to hope to get a positive real number. And the limit I'm taking is the sequence here, sine n, that absolute value, over 1 over n squared, right? And what do we get?
Just the absolute value of sine n.
Yeah, limit as n goes to infinity of the absolute value of sine n, right? And if you let n go to infinity here, this is not headed to a single number. It's oscillating, it's jumping up and down, right? This is not headed to a number. It's not headed to infinity either. It's just not headed to a number. This limit doesn't exist. Shit, what does that mean? Does not exist. What does that mean?
Divergent?
No,
Test fails.
that test failed. Y'all wanted to do limit comparison. I went for it. It didn't work. Okay? We can't draw a
Wait, so
conclusion.
I have a question. Why are we only just looking at sign and not the
Reciprocal.
n?
1 over n
Oh.
squared flipped up, the n squared's canceled.
Yeah, they canceled out.
Yep. Okay, so you know what? I don't want to give up on this. I don't want to give up on this because we went and we did the limit comparison because I think we had all agreed maybe at the end of class last time that this seemed to be the preferred method if it works, because it's pretty quick. But since it didn't work, I'm going to go with this one because for this one, I'm comparing it. CJ, I think, said, let's compare it to 1 over n squared, which is convergent. So we just need to show that this inequality is true. Okay, so let's see if we can show that this inequality is true. Maybe we'll get lucky. So instead, I want to show that absolute value of sine n over n squared, what do we say, has to be smaller than or equal to 1 over n squared. Does everyone understand what I'm doing? Now, just, I don't know, multiply both sides by n squared. Just multiply the left side by n squared, right side by n squared, cancel, cancel, cancel. What do you get? Absolute value of sine n less than or equal to 1. True or false?
True.
Is the sine function, absolute value of it, is it always less than or equal to 1?
Yes.
Yes, that's true. Therefore, whatever this does, that does, right? Therefore, this sum converges, which implies by the theorem that the sum without the absolute value converges. So that example shows you how you can use the absolute convergence of a series along with a comparison test to show some other series converges. I think it might be worth running through that one more time. We started out with something. It was not alternating. Look, everyone, if this had been an alternating series, I just would have run the alternating series test. That's what I would have done. But it's not alternating. It does fluctuate between
अबे
positive.
भाई ये drop.
What? Okay. So it's not alternating. So I said, all right, let's see if it's absolutely convergent. Because if it's absolutely convergent, if this converges, then I know that that converges because, well, that's what the theorem just said, okay? So we went ahead and looked at it. We said, all right, well, does this converge? And we said, oh, I don't know. Let's compare it to something. Oh, let's compare it to this. We know this converges. And then we tried the limit comparison. We got that it didn't exist. We were hoping for a positive number here. It didn't happen. We didn't give up. We went back to the good old inequality way. When we did that, it worked. So this told us that that converged. And once we know that that converged, well, that forces the original one to converge. Okay. I think the moral of that story is just be careful that sine of n is not an alternating series. Sine of n is not an alternating series. All right, the ratio test. And you know what? Before I do the ratio test, I want to talk real quickly about this theorem. It said if your series, if you have a series that's absolutely convergent, then that means that the series itself is convergent, right? That was the theorem I gave you, right? So I want to talk to you a little bit about logic, okay? Just logic. In logic, this could be looked at as a statement. If this is true, so if P, then this statement is true. If P, then Q. So those of you who have done any logic would have seen this before. Another way you could write this is P implies Q. So all I want to stress here is, I'm not going to get in this big argument about or big discussion about logic, is just to understand that implications like this, that's what they're called, implications, they do not work in both directions. So I'll give you an example. Do you agree with this statement? If you live in the United States, okay, so I'm just going to write this. If you live in the US, that means you're physically standing in the United States of America, right? If, you know what, hold on. I almost did this wrong. If you are standing in Texas, sorry, then you're in the United States. So if I'm standing somewhere in Texas, then I'm standing in the United States. Do you agree with that statement? Okay. Well, at least now, until Texas secedes from the Union, which who knows, that may happen at some point. Does it work the other way around? Can you reverse this? If you're standing in the United States of America, then can you guarantee me you're standing in Texas?
No.
No. So implications only work one way. So the way we write this is Texas implies you're in the United States. But being in the United States does not imply that you are standing in Texas, right? So you have to be real careful with theorems because they work one way but not the other. So when you read this, if you're absolutely convergent, then you're convergent. You cannot read this the other way around. You can't say, oh, if you're convergent, then you're absolutely convergent. It doesn't go from right to left, it only goes from left to right. Okay? Now, there are some mathematical statements that do go in both directions. Some do. And when you see them, they do something special. So here's one. If No, okay, yeah. If x equals 2, then x cubed equals 8. That is a statement that goes in both directions. So do you agree that if x is 2, then if I cube x, I'm going to get 8? Right? But if I tell you it the other way around, if some number cubed is 8, then x has to be 2 also. So do y'all agree I can write this the other way? Now we're only talking about real numbers. If you bring imaginary numbers into this statement's not true, but we're not talking about imaginary numbers. Okay, so do y'all agree that this can be said either way? Right, yes. So here's the way we would write it. We would write x equals 2 IFF x cubed equals 8. So if you see IFF, what it means is if and only if. This basically means this goes both directions. You can read it from left to right, or you can read it from right to left. And sometimes you'll see that instead. You'll see an implication arrow in both directions like that. And that means that this implies this, but this also implies this. Would this be true? Would this be a true statement or not? X equals 2, implication both ways. There, would that be true? Would this be correct for me to write this?
Yes.
Sure,
Yes.
sure. Now, if I
Well,
tell you
actually-
x is 2, if I tell you x is 2, then I agree x squared must be 4. But if I tell you x squared is 4, that doesn't mean that x was 2. It could have been -2,
Could have been -2, plus or minus.
right?
Right.
It could have been. So the implication does work. This from left to right, yes, that works. But right to left, not always. That's why I used cubed up here, because cubed, the only way you can cube a number and get 8 is if that number started out to be positive. Okay, this is just a little small detour on logic. We're not going to, unless you'll like this. How about this one? If x squared equals -1, then x.
So this is about the logic behind the absolute test, right?
No, this is just about logic in general.
Oh,
Just
okay.
in general, the way logic works. If x squared -1, then x equals 4. Just look at this statement. And I just want to tell you right now that we're only talking about x as real numbers, okay? So right now, you're only allowed to think about real numbers. Is this a true statement? If x squared equals -1, then x equals 4. Is that true or false?
False.
False?
Yes.
Seems like it would be, right? So have any of you taken logic? If you have, you might know what this is all about, but this statement is actually true. Because your assumption here is false. It's impossible to take a real number and square it and get -1. So your assumption is false. Anytime your assumption is false, your conclusion has to be true, which is crazy, but that's the way our logic system works. If your assumption is false, your conclusion is true. And we would say that this statement is vacuously true. All right, we're stopping. I can just keep going on with logic all day. One of my favorite ones is this one. Is this statement true or false? All the pink elephants in this room have wings.
True.
It's true. Yeah, all the pink elephants in this room. See, I'm in my office right now. All the pink elephants in this room have wings. That is a true statement. And the reason it's true is because in order to show it's not true, you would have to find a pink elephant in this room that doesn't have wings. You would have to find a counterexample. I don't have to provide you the pink elephants with wings. I don't have to prove that they exist. You have to prove that there's one in here that doesn't have wings. Or maybe you would find a blue elephant in this room with wings. See what I'm saying? Logic is weird. When you start getting into it, logic is really weird. You want to do one more? I can do another one.
Yeah.
Okay, so listen to this one. Cameron looks like he's in deep thought over there. Okay. So I'm going to have Cameron's going to have the theme of this one then. Cameron cuts the hair of everybody in San Antonio who doesn't cut their own hair. Okay, Cameron cuts the hair of everybody in San Antonio who doesn't cut their own hair. Say it one more time. Cameron cuts the hair of everybody in San Antonio who doesn't cut their own hair. Who cuts Cameron's hair? So could it be Cameron?
No,
Why?
because I don't know why. I just know that it's not Cameron because Cameron does not cut his own hair. So someone else would have to cut his own, like,
Okay, so Cameron cuts the hair of everybody who doesn't cut their own hair, right? So can he cut his own hair? No.
Yes.
No, because then he would
No,
be cutting his own
no.
hair.
Then if Cameron cut his own hair, then he would be cutting the hair of somebody in San Antonio who cuts their own hair.
own hair, exactly.
Okay. Okay. So could it be somebody else? Could
Or
somebody else
Cameron
cut Cameron's
doesn't
hair?
cut his hair then.
If somebody else cuts Cameron's hair, then that means there's somebody other than Cameron that cuts someone's hair in San Antonio who's not cutting their own hair. But Cameron's supposed to be the one who cuts the hair of everyone who doesn't cut their own. It's a freaking nightmare logical maze. Okay.
Yes, because I don't live in San Antonio.
Okay, there you go. Yeah. So look, logic is just really weird. You can start to get into these weird just plays on words. You've probably heard ones. I don't know. Okay, we're moving on. Ratio test. Deep breath. This is the biggest test of them all. This is the big daddy. This is the almighty ratio test. All right. And the thing that makes this ratio test so awesome is it works on any series. It could be alternating. It could be, doesn't matter what the series is. We don't have to look for, is it plus or minus, or it works for everything. All right. So the test goes like this. Given a series, right? Okay. So we're given a series. Here's what we're going to do. We're going to take the limit. Okay. We're going to take the limit as n goes to infinity of a sub n plus 1 over a sub n, and we're going to take the absolute value of that. So think about what this is saying. We're going to start with our series, and we're going to just look at the sequence. And we're going to take the ratio of the n plus 1 term in the sequence over the n term. So it's like, it's the number right after the previous one. We're going to take their ratio. We're going to take the absolute value, we're going to take the limit and let n go to infinity, and we're going to look at the answer. Okay. So this limit, we have 3 different outcomes that could happen. If that limit, I'll call it L, if L is less than 1, then we have convergence of the series. We have convergence of the series. If the L is greater than 1, we have divergence of the series. And if L is equal to 1, the test fails.
It really is the big papa of tests.
Yep. Mostly, again, because it handles just about everything. Just about, not everything. I mean, it is, we are going to use this almost exclusively in the next sections. Almost exclusively, this is what we'll be using. All right.
So if it fails, then we try to decipher what other series, other
What
tests
other
can
tests? Yeah, then you might go to another test.
But what is the probability of this test failing?
I don't know, probability. I can't give you a percentage.
Like
Let's
hypothetical.
just do this. Let's look at the problem we just did. Look at this one right here. Okay, we know that this series converges, don't we? We've done this problem already, alternating series test. You could also take the absolute value of this. If you take the absolute value of this, you get 1 over n cubed. That's a p series. P is 3, greater than 1. It converges, right? Absolute convergence implies convergence. I know I'm talking fast here, but there's several ways we could show that's convergent. But let's act like we didn't know that. Let's try this ratio test. So what I do is I take the limit as n goes to infinity of, well, what we have to do first is take this and do the n plus 1 version of it, which means replace everything with n plus 1. Now be real careful on this. -1 to the n plus 1 over n plus 1 cubed over -1 to the n over n cubed. Y'all see what I did here? Any questions? This part up here is that, and the part on the bottom is the original sequence. Now, do I really need to care about the -1s anymore?
No.
-1 to the n, -1, those are going to, absolute value of that, it's not going to matter, right? It's not going to matter. So I'm just going to get rid of those. So I get 1 over n plus 1 cubed over 1 over n cubed. And when I flip, this becomes limit, n goes to infinity of n cubed over n plus 1 cubed. And now you have infinity over infinity, right? And if you do this L'Hopital on this, it's pretty clean. You're going to get 1. Which would mean what?
Test
Convergent.
fails.
The test failed.
Oh,
So
it failed.
you were asking, right? You were asking, like, what's the probability? Well, look, I just gave you a problem that it failed, right? So, but the issue is this. This is not a hard series to figure out. Like, we can figure this series out. Look, if the ratio test, if this test were if this was like the vaccine for the virus of series, then this is all we would teach you, right? This is, we'd just be like, here's the way we test series. This is the big daddy because it works a lot of the time, and for where we're going, it works every time for where we're headed. This test is good enough for what we're going to be doing. All right. So let's see this test work in action, because now you're discouraged because it didn't work the first time we tried it. So let's see it operate on something interesting here. How about this one? Sum n equals 1 to infinity of -1 to the n times n squared over 4 to the n. Okay, let's just appreciate a couple of things here. If we didn't have the ratio test right now, we would probably have to do like an alternating series test, because we do have an alternating series. But maybe we would just take the absolute value of this to not even consider that, and then look at n squared over 4 to the n, and maybe do a comparison like we did last class. And maybe we compare it to like 1 over 4 to the n, because the 4 to the n kind of dominates things here. Maybe. Screw it, let's go with the ratio test. All right, let's try it. Let's see if we get anywhere. Ratio. So I need to take the limit as n goes to infinity of this thing, of the absolute value, don't forget the absolute value, of this thing with n plus 1 plugged in, over just that thing without, with just n. they call it the ratio test because you're always going to be taking the limit of a ratio, right? Sorry, I meant to take that pole off of there. All right, I'm going to completely ignore the negative ones to the ends now. I don't need to worry about those. I'm also going to flip fractions. So I have on the bottom, I've got this n squared over 4 to the n. I'm going to flip it and bring it up, still keeping my absolute value. So how about this? N plus 1 squared over 4 to the n plus 1. But then I brought the bottom one and flipped it. So that means I have a 4 to the n on top. And on the bottom, I have n squared. This is a good opportunity for you to ask any questions about algebraically how I got this. Right now, if you take the limit, you're going to get like infinity squared over 4 to the infinity. That's infinity over infinity. You've got times infinity over infinity. Right now, it's still too big of a mess for us to do anything with. So let's do some algebra.
So what if we combine n plus 1 and n and raise it to the power 2? And then, but then it's going to be the same thing.
Yeah, I'm going to do this. Do you see me rewriting 4 to the n plus 1 as 4 to the n times 4?
Mhm.
Right? You see that? This is going to happen a lot of times when you use the ratio test. The 4 to the n's now cancel. Right? Okay, what do I still have here? I have a 4 on the bottom, right? 4n squared. And on the top, I have n plus 1 squared, don't I? So let me FOIL that. That would be n squared plus 2n plus 1 if I FOIL out the top. Infinity over infinity. What do you think?
L'Hopital's rule.
L'Hopital? Okay, what would happen if I did L'Hopital once?
So it'll be 2n plus 2 over 8n.
Okay.
Then
Infinity over
another
infinity.
L'Hopital rule.
Another L'Hopital.
So you get 2 over 8, which is 1 over 4. And this converges.
Because it's less than 1, right? Because it's
Yes.
less than 1. Therefore, we have convergence. So that means the original series converges. Because the ratio test spit out a number less than 1/4. I mean, sorry, less than 1. Now, are we saying that this series, are we saying that this converges to 1/4? Is that what we're saying?
No.
No, no, not at all. All we're saying is that it converges, all right? We still don't know what it converges to.
But so geometric and telescopic and absolute test only tells what it converges to.
Yeah, the only things we can ever find the sum of is a geometric and a telescopic. That's it. Those are the only 2 types of series we could ever find the sum of. Okay, I have another one for us. This one is going to be nice. I'm going to put it up here. I'm going to let you look at it, and then we'll talk about it.
So would it be a good idea, like if you don't know where to start on a problem, to first do the nth term test and then like hop onto the ratio test?
You know, I don't know. I mean, I guess I could say yes because it is such a great test, but you know, like if it's a P series, like you wouldn't want to go through all this work, you know? Like you just be like, oh, it's a P series. Or if it's something simple to compare it to, like the problem I did, the one right at the very beginning, right, that I showed it failed. Well, we should have just done that with the alternating series test. That would have been easier just to do it that way anyway. So I don't know. I don't want you to box yourselves into like a certain thing. I want it to be more, or it should be more for you, like you're seeing it and you're going, you know what, I think I want to go down that road. I don't want you to always be like, I'm going to go down ratio test road every time. Because you might just take up too much of your time doing it that way.
Okay.
I don't know if that's okay. I mean,
Yeah, no, I'm just I'm saying like if we don't know like which test to use,
Yeah, I mean, if you're not sure, then try ratio, but then, you know, just be prepared to be disappointed if you get one and just be like, okay, well, I gotta try something else then. You know? Okay, so look at this one. Oh, I was gonna let you look at it for a few minutes. Maybe like 2 or 3. I'll let you see what you come up with. All right.
I
Already?
think I got some of it, at least where I can like cancel out things.
Yeah, so we're gonna run the ratio. So you go n+1 factorial over n+1 raised to the n+1. Be careful there. All over n factorial over n to the n. And then on your next line, you'll go ahead and flip the second one up. So you'll have n+1 factorial over n+1 raised to the n+1 times n to the n over n factorial.
So right here, I canceled out the n+1 because factorial is basically n+1. It's n-1, right?
This becomes n+1 times
And
n
then-
factorial.
Yes.
And then
So,
the n factorials cancel. You're still left with an n+1.
Then next, I split the n+1s in the denominator.
Yeah.
You did what?
Cancel out. You like split the exponent into
Okay,
2.
yeah. I see what you're saying. So
So what was the move you made, Professor? To get
Sure.
n+1? Yeah.
to get it to cancel,
Yeah.
I'm using the fact that n+1 factorial is equal to n+1 times n factorial. Now we did talk about that. Trying to remember when we did that. Oh man, this would have been 8-1.
It was 8-1.
Where is it? Where is it? Where is it?
I'm pretty sure it was on 11.3.
It was 11:30. Yeah, I'm thinking it was also. I may not have scrolled up all the way. Right before that. There it is. Right here.
Okay.
Yeah. So you can see that this n+1 factorial over n factorial turns into n+1. See, that's why I showed it to you back then, because I knew it was coming, right? So here it is. All right, so now we continue, yes?
Yes.
I was told, let's see, you did on the bottom, so we still have an n+1 up here. On the bottom, I'm being told split that into n+1 to the n times n+1, is that correct? Is that what you did?
Yes. Yes.
And then times, we still have an n to the n here and then over 1 like that.
So is the n plus 1 still a oh, no factorial then?
Yeah, those are gone, right? And so we have, let's see, n to the n over n plus 1 to the n. Crap. That's still infinity over infinity, isn't it? So it's-
Can you do,
No, hold on. I need to be taken out back for a minute and straightened up. I forgot my limits. I will suffer for that in math hell when I finally arrive. Okay, there we go. So we still have infinity over infinity. Now, watch what I do here. Go ahead, Minato. Someone say something?
Hospitals?
Not yet. No, thank you. I'm not quite sure I want to do that yet. That just seems like torture. I'm gonna rewrite
what
it.
if, what if you do a geometric here?
Okay, so like kind of like this, rewrite all this to the n power.
And then do a geometric, yes.
Well, we're not doing a sum though. We're not doing a series. This is not a sum. Anymore. It's just a limit. But even if it was, this is not a number. This would have to be a constant. It would have to be like 1/3 or something like that. This is impacted by n. So look, do y'all agree right now that if I take this limit, the form that I'm getting is that what's in there, that goes to, I can do L'Hopital on that, that goes to 1/1, that's 1, and then to the infinity? Okay, anytime we see this, we have to do a special type of limit. We have to do something. So I'm gonna write it down here. So here's what we're focusing our attention on right now. I'm gonna take the absolute value away. Does everyone understand why I'm taking the absolute value away? This is positive no matter what, right? So the absolute value really doesn't matter. Anytime we get a limit that looks like 1 to the infinity, what we do is we call the limit something like y. And then we bring natural log in on both sides. Do you all remember it all us doing this?
Yes, and bringing the n out in front.
And I remember when we did it last time, you were the one who said bring the n out front. So we take the natural log on the left and the natural log on the right, the n pops out in front. And now if we look at this, this is going to look like infinity times 0. Because this goes to infinity, and then this turns into a 1, and natural log of 1 is 0. So here's the form we have now. You all remember what to do with that? Whenever you have infinity times 0 in a limit,
L'Hopital?
not yet, it has to be.
Oh,
Yeah,
upon, it should be in a ratio.
Yep. So how do I make that a ratio?
So ln n.
Remember this idea of
Divide by
taking
n?
one of them and dropping it? Taking
Oh, yeah.
one of these and dropping it to the bottom?
Wouldn't it be just n?
What? Well, no, if
the-
you're going to put it on the bottom, it has to be 1/n.
Okay, yes. Yes.
Okay, pretty messy stuff here, if you ask me. Okay, so now I have the form that the top goes to 0, and now 1/n goes to 0, and finally I have 0, 0. Now I can do L'Hopital. Yes, I have to take derivative of the top, everyone.
That's
Right.
1 over n. So it's n plus over n.
Yeah, so it's one over this, right? It's 1 over that. So I'm just going to put the reciprocal of it, n plus 1/n. Times, don't forget, chain rule. Now you have to take derivative of what's in here.
Which is a n, 1.
Quotient rule.
Oh,
Yeah. Derivative of the bottom is -1/n squared. Okay, recap. Derivative natural log of something is 1 over it, so I just wrote it as the reciprocal, and then the derivative of it in here is a little quotient rule I have to run. The derivative of the bottom is just this. And now it's, you know, at this point, it's just some algebra. Well, I say some algebra, it's cleaning up time. Let's clean up. So n plus 1 over n times, let's see, what is the numerator here? N plus
Plus
1
1 minus
Isn't that just n
n.
plus 1 minus n? Isn't that just 1 or minus, sorry, just 1? That's just 1, isn't it?
Yep.
Yeah, that's just 1. 1 over what? N plus 1, n plus 1 squared, right?
But doesn't the n plus 1 cancels out?
They're here?
Yes.
Yeah, they will. I'll do that on the next line. And then all of that's over negative 1 over n squared. Let's cancel an n plus 1. We're almost there, everyone. We're almost there. They won't all be like this, okay? They won't all be this complicated, but let's see what we have. So what's left on top? I have 1 over n times n plus 1. And on the bottom, don't I still have this guy right here? The green? So I'm going to flip him and bring him up. So he's going to be n squared over negative 1 right there. Can't believe I'm almost out of room here. Natural log y equals limit n goes to infinity. Okay, on top I have n squared. On the bottom I have negative n squared minus n. Where did I get that from?
You just cross multiplied? I mean, just multiplied them?
Distributed here, right? Got n squared plus n, then hit it with the negative 1. And now I have infinity over infinity. So
Then
L'Hopital,
another L'Hopital.
natural log y equals by L'Hopital limit n goes to infinity. Derivative of the top 2n, derivative of the bottom,
Negative 2n.
negative 2n minus 1, right? L'Hopital again. Please tell me it's not true. This is true.
And
This
it's
is-
1.
Yeah, negative 1.
Negative 1. Okay.
So natural log of y equals negative 1.
So we're in business.
Yes. Now e on both sides to get rid of the natural log. So what is y?
So
1 over e, right? 1
Mhm.
over e. I'll give you just 10 seconds to write this down or catch up because we need to draw a conclusion here.
So real quick,
Yeah.
like if you go straight to the left from where your cursor is, right there, couldn't you have canceled one of the ends?
Yeah, I probably should have, huh?
Like, would
Yeah,
that have,
that probably, I didn't see it right away, but yeah, we could have gone n here and then right there, L'Hopital from there. Yeah,
okay.
yeah. We still would have got negative 1. Okay, so what was y? We said y is 1 over e. Okay, what was y? Y was this limit. What was that limit? Oh, that was this thing we were trying to look at. And what do we need for convergence on the ratio test? We need that limit to be what?
Less than
less
1.
than 1.
Less than 1. So this limit we just found is 1 over e. Is 1 over e less than 1?
Yes.
Yes. So this is a convergent series.
Okay, question.
Yes.
So remember where we brought in the natural log ln? So, what is the simplification? Like, when do we use this? I know how to use it, but I've never. Okay, when?
When do we use the natural log on both sides?
Yes.
Whenever you take a limit and get 1 to the infinity, 0 to the 0, infinity to the 0. You see, those are all indeterminate forms. 1 to the infinity,
Okay.
0 to 0, infinity to 0. It's not everything you can think of. Like if you do infinity to the infinity, well, that's just infinity. If you do 1 to the 0, that's just 1. So that doesn't work. So it's not everything you can possibly think of. It has to be an indeterminate form.
Okay.
Okay, we have more to do. I've got 6 minutes. I'm not going to get to another example. I want to show you something, okay? I want to show you something. So you can kind of like just relax for a minute, all right? Do you all think that sum converges or diverges?
I think it converges.
What would it converge to if you think it converges? Do you have an idea?
I don't want you to say like pick me on again, but I thought it was 0.
You don't want me to what? Get the whip out? Is that what you said?
No.
No, man. I mean, look, I'd rather have people responding than not responding. It doesn't matter. Look,
So yeah,
you're
but
saying 0. You said 0?
Yeah.
So I think your idea here is that, these two are going to cancel, these two are going to cancel, these two are going to cancel, and that'll keep happening forever, right?
Would it be
Yeah.
infinity?
Okay, so let's first all understand, but do you understand 0 is possible? Like, that seems reasonable. Okay, how about this? What if instead of doing that, I took those two and the next two?
Then it'll be a 1.
Then
It
it'd be
would
1, right?
converge to 1. Yeah.
So I don't know, maybe it doesn't converge to anything. I don't know. It's just more of a thought exercise at this point. So let me see if I can convince you of this. Let's just call this S, okay?
Okay.
Let's say it converges, all right? Let's say it does. I don't know if it does, but let's say it does. Then just follow the algebra that I do right here. If this is true, so if that's true, then do you agree that S could be rewritten this way? Like that. Do you agree I could rewrite S this like this? Just putting a
Yes.
0 in front, right? Yeah?
Yes.
Okay, now I'd like for you to add these straight down. So what's S plus S?
2s.
2S. Okay, start adding here. What would you get if you added those two? 1.
1.
Right? 1 plus 0, and then plus, what would the next one be?
0, 0,
Zero.
0.
0, 0 the whole way, right? And so wouldn't it be 2S is equal to 1? And if you
Which
divide
is a
both
half.
sides by 2, you get a half, don't you? And that
Yes.
means we're saying that sum is equal to a half. Which is kind of weird because first we said it might be 0, right? If you write it like we write it this way, they all kill each other off, so you get 0. But if you write it this way, those killing off, then you get 1. So is it 0 or is it 1? Well, it looks like maybe it might be the average of the two, right? Halfway between. It's kind of weird, isn't it? Isn't that weird? Okay. We've just begun. Okay, so now I want you to look at a completely different series. I want you to look at this series. 1 minus 2 plus 3 minus 4 plus 5 minus 6 forever. All right. Do you think that converges or diverges?
I think that diverges.
Yeah, maybe. It seems like you put these two together, you get -1, right? But then put it together with that, now you're at 2, but then you take that one away and now you're at -2, but then you add that, now you're at 3, and then you take that away, you're now, does it seem like the negatives are going to start to dominate maybe? Maybe, yeah, maybe. Okay, so watch this out, watch this. Let's call this something, let's not call it S, let's call it M, okay? Let's call this M. If this converges to M, do you agree with this? What's 4 times M? Oh, wait a minute, hold on, not 4. I've forgotten. What's 2M? I'm gonna do it this way. Let me do this. Let's write M again, okay? Let's write M again, but let's write M like this. I'm gonna go 0 plus 1 minus 2 plus 3 minus 4 plus 5 minus 6. Do you see what I've done?
Mhm.
I've rewritten M, but I put a 0 here in front. Now add down again. What do you get if you add down?
2m,
2M equals what?
1.
1, not, okay, be careful here. 1, that's this, right? This is 1. What
Then
about
plus
these two?
1.
-1.
Negative
-1.
Minus 1, what do you get here?
1.
Plus
Plus
1.
1.
Plus 1.
Here.
-1.
Okay, next one.
plus 1.
Oh, shit.
Then-
Y'all recognize that? What is 1 minus 1 plus 1 minus 1 plus 1? What is
It's
that?
just this above series.
That's S, right? That's S. That's this guy. And what did we say S was?
1/2.
Was a half, right? So that means that 2m equals S, but that means 2m equals a half. And if I divide by both sides by 2, I get m as a fourth. Shit. That means that this thing up here adds up to be 1/4. Okay, your mind should be blowing right now. You should be bleeding out of your ears. 1 minus 2 plus 3 minus 4 plus 5 minus 6 is going to add up to be this fraction.
But how?
Yeah, okay, yeah, great question. I mean, but do you all understand the algebra I'm doing here? You can leave if you need to leave. I'm going to show one more. This is the one that'll blow your mind completely out of the water. Okay. I want us to look at this. 1 plus 2 plus 3 plus 4 plus 5 plus 6 forever.
This is divergent for sure.
Yeah, yep. Wait till I show you what it adds up to be. You ready? Let's call this, I don't know.
G.
I was gonna go C for crazy because this is gonna be crazy. All right, you ready? So here's what I'm gonna do. I'm gonna take that C and I'm gonna multiply it times 4. Don't ask why, just do it. Okay, so if I multiply that times 4, I get 4 plus 8, right? Plus 12 plus 16 plus what?
20.
24, 28.
24, right? Okay, now,
You
hold
missed the
on.
20.
Wait, I missed something. Yeah, 20
20, 24,
plus 24. Hold on.
and then 28.
Hold on just a second. I've lost myself a little bit here on this. Give me a moment. I'm going to reference my notes because there's a, I need to do it. I need to do a subtraction here, but I can't remember what it is. So I'm going to need to look at my notes real quick. This, by the way, is a very common problem. Not common, but it's, you can find this out there. Let me see here. Okay, I know what I did wrong. Okay, so look, we're gonna wait on this 4C. That's what it is. Hold on. From this, what we want to do is, let's take this, and I'd like for us to take M. Remember what M was? Right? M was this. I'd like for us to subtract that M. So subtract M from this. So what would happen if you subtract M? That means you're going to subtract, what is it? What's M? M was 1 minus 2 plus 3 minus 4 plus 5 minus 6, right?
Mhm.
So let's go ahead and do this. What would happen if I took 1? So I'm going to do these kind of vertically. What would happen if I took 1 and then I subtracted 1? What would I get?
0.
0, okay. So this is, just so you know, this is C minus M. So I get 0, and then what would happen if I do the next one? I go 2, but then I take away -2. That would be the same as adding
4.
2. That'd be 2 plus 2, that'd be 4. And then next one would be 3, and then I take away 3, which would be 0.
0.
And then the next one would be 4, and I take away -4, which would be adding 4, which would be 8.
8.
And then the next one would be 0. The 5s would cancel. And the next one would be what,
12.
12, okay, and then 0 again, and then next one would be 16, right? You see the pattern?
Mhm.
Yes, it's doubling, but how would you get the 0 in between?
How am I getting these zeros?
Yes, like if you try to drive out a formula for it.
Well, wait, just let me do it. Hold on, watch. So do you agree that this is 4 plus 8 plus 12 plus 16
Yes,
plus the next one would be 20?
yes,
Now, do you agree that I could factor a 4 out of all of these?
yes,
And if I factor 4, I'm going to get 1 plus 2 plus 3 plus 4, right? Plus 5 plus forever, right? I forgot the dot dot. But do y'all
But it's-
recognize this? What is
this is the
this?
same thing, same
This is
thing as
Or
C.
C.
That's C, right? So what we have is this, C minus M equals 4C. Okay. Let's subtract C on both sides. We get negative M equals 3C. Right? Subtracting C on both sides.
Mhm.
But what was M? We did M earlier, didn't we? Said here's
1
M,
over
and I convinced you that M was what?
1 over 4.
Okay, so this means that negative 1/4 equals 3 times C. And now if you divide both sides by 3, you get negative 1/12 equals C. Which means that what we're saying is 1 plus 2 plus 3 forever equals negative 1/12.
But how?
Yeah.
What?
Look, I've gone way over on time. I just wanted to show you this because it looks crazy, doesn't it?
It
This is
does.
absolutely insane.
But now I'm curious, how is it even happening now?
It's not happening. All the algebra I've done is correct, okay? Like everything I've done is correct, but we made some huge assumptions here. We assumed that this series up here, we assumed that that series converged, right? We assumed it. So we said, let's call it S. It doesn't converge. So you can't call it S. All right. Do you remember this? Do you remember this thing where we had the series and I said, look, if you have a series and you've got two things being added inside, can you split it into two?
No. Yeah, you can.
If these diverge, you can't, right? This is the same sort of principle. If we have series that are divergent, you cannot manipulate them algebraically and trust your answers. But this is a cool thing. You can go take this to your friends and you can try and convince them that, you know, this is 1/2 and this is 1/4 and this is negative 1/12, because it's hard to see the mistake in here. The mistake is not in the algebra. The mistake is in
The assumption.
assigning a value to this. You cannot assign a value to this sum. You can't call it C. You can't. It's not a number. It's a divergent series. So, but it's cool. It's a cool little trick, I guess. All right. Homework wise, I mean, y'all need to just work on the 8-4. Make sure you got 8-4 taken care of. Oh, no. 8-4, we haven't finished 8-4. 8-3 for sure. Make sure you've got 8-3. And you can start the 8-4 homework. At least just go through and see how it goes. All right, everyone. Any
All right,
questions?
thank you.
No questions. Thank you very much.
Okay, have a good one.
Thanks.
I have a question.
Thank you, you too.
Are you having office hours tomorrow?
Let's see, tomorrow's Friday.
Yeah.
If you text me, get my cell phone number off the syllabus, text me what time. I don't have official hours tomorrow, but I'll be around. Are you looking at like daytime or afternoon, evening?
Evening, definitely, because I got some work to do tomorrow.
Evening?
Yeah.
Okay, well, text me. It's Friday, so I'm gonna have to see, you know, I don't know what my plan is yet, but if you text me kind of earlier in the day, I can give you an idea if I'll be free.
Okay.
Does that work for you?
Well, I might be asleep early in the day, but okay.
Oh, or text me today and tell me when tomorrow, you know?
Okay. Yeah.
I think it's going to be too early for me to tell you anything until tomorrow because My wife gets some medical treatments every 3 weeks, and she's getting hers today.